Welcome back to Honors Calculus. In this video, we're going to be looking at the fundamental theorem of calculus. That's a weighty title, and it has a weighty implication in our study of calculus, not just in what we're doing here, but continuing onward through the entire sequence of calculus courses. Before I get into the fundamental theorem of calculus, I want to talk about a couple of fundamental theorems that you've seen before. You probably didn't call them by name, but I am certain that in your previous mathematics coursework, you have come across the fundamental theorem of arithmetic and the fundamental theorem of algebra. The fundamental theorem of arithmetic tells us that every whole number, can be written uniquely as the product of prime numbers. Every whole number has a unique prime factorization. And that is the basis of so much of what we do in arithmetic. From there, we learn how to use prime factorization to find the greatest common factor and least common multiple of a pair of numbers. We use those tools to be able to work with fractions, to be able to simplify expressions, and even go into algebra and learn how to factor polynomials. The fundamental theorem of algebra probably comes after you really have learned to use it, but the fundamental theorem of algebra tells us that every polynomial equation, if the polynomial has degree n, then there are n solutions to the equation if you count multiplicity. And that's how we solve equations. If the equation is not a polynomial equation, if it involves radicals, if it involves fractions, we do some manipulation to the equation to rewrite it so that it looks like a polynomial equation. We then factor the polynomial. And we know that a polynomial will factor into linear or quadratic factors. The linear factors are degree 1 and all have one solution. The quadratic factors are degree 2 and all have two solutions. Generally, if it can't be factored into linear, that means that the quadratic factors have complex conjugates as the solutions. And we know that if we add up the degrees of all of the linear and quadratic factors, we get the degree of the polynomial we started with. So there is the fundamental theorem of algebra, is the driving force of everything we know how to do to solve algebraic equations. The fundamental theorem of calculus, in kind of the same way, at first glance, seems like it's kind of an offshoot. It's an odd thing to be looking at, but we will quickly build up the framework we need to make it incredibly powerful. Let me get my head out of the way and let's start doing just that. We're going to start off with an accumulation function. Remember from previous work, an accumulation function is any function big F of x, which is defined by an integral. We generally start at 0, but we can start at any starting point. That's a constant. I'll call it x naught to be generic. And we end at our variable, our independent variable x. And we're going to integrate some other function, little f, called the density function. And we want that at some dummy variable. I usually use the dummy variable t, so this is little f of t dt. And I claim that if I want the derivative of this function, I am going to take the derivative of the accumulation function is the density function just evaluated at x instead of at t. And wow, is that going to be easy to calculate these derivatives? But it is a theorem. And so if it's a theorem, we have to prove it. All right, I'm going to be a little bit fast and loose with this proof. I think that seeing the graphical proof is going to make a lot more sense than a more analytic proof. But if you are curious, I'm happy to provide some more details on the analytic side of the proof. But let's consider the graph of some generic function f of x. Let's mark in where our x naught is. Let's mark in where our point of interest x is, and let's take the space enclosed, and we know that that space is f of x, right? The integral, the accumulation function, is defined as the area under the curve. And then here's where I'm going to get a little bit interesting. I'm going to take just this tiny little sliver, call that delta x. And if I take that, then I know if it's a small enough sliver that big F evaluated at x plus delta x is equal to the area that's in yellow, which is f of x, plus the area that is in blue. Well, I don't quite have a formula for that, but if I take a small enough value of delta, I can again approximate that this thing is a rectangle. Its height is the value of the function, so that will be little f of x times the width, which is delta x. And with that in mind, the definition of the derivative says that big F prime of x is equal to the limit as delta x goes to 0 of big F of x plus delta x minus big F of x all over delta x. And substituting in what we just figured out, big F of x plus delta x is big F of x plus little f of x times delta x. And look at what happens. We've got a plus f of x and a minus f of x. Those things cancel each other out. Then we've got a delta x over delta x. Those things cancel each other out. And we got rid of all of the delta x's, which means that the limit as delta x goes to 0 of f of x is just f of x. All right, so again, it's not a foolproof proof. There are some nuance happening here, some approximations that I've made that technically speaking don't quite work, but I think that that really gets the point across, seeing how we're talking about area and we're talking about how the area changes. And thinking about that, thinking about taking a small enough region, approximating it as a rectangle, gives us a nice tool for working through this. And so, if I want to take the derivative with respect to x of the integral from 7 to x of x squared times the sine of x, I'm sorry, I should do this the way that I normally write them out. We need to have a different variable in here. I'm getting ahead of myself. We need a dummy variable. because x is the limit of integration, and we don't want the confusion of that with what's happening inside. Once you get beyond calculus, especially if you're going into physics or engineering, we stop caring about that because we know how to deal with the same variable having two meanings in two different places. And we know the fundamental theorem of calculus, so we know it's not going to last very long anyway. But we should be technically precise about it. But we can use the fundamental theorem of calculus here, which tells us that all we have to do to take the derivative of this integral is take the argument inside and evaluate it when t is equal to x. So just replace the t's with x's, you get x squared sine of x, that's the value of the derivative, or that's the expression for the derivative at any point x. Once you have the fundamental theorem of calculus, trying to evaluate the derivative of an accumulation function is the simplest task that I can ask you to do in the course. All right, that's impressive, but I still haven't really established why accumulation functions are so valuable. They are valuable. There are a lot of places where accumulation functions have a lot of usefulness, but getting into that is a little bit beyond the scope of the course. In fact, my task for the rest of this course is to try to convince you that no matter what kind of integral we have, we can force it to be rewritten as accumulation functions. And so to get there, I have one other theorem that I want to talk about today. And it feels like it is completely out of nowhere. And honestly, I probably shouldn't even call this a theorem. Let's go ahead and call this a lemma. It is a theorem. It is something we are going to prove, but it doesn't really stand on its own. It's very technical. Well, it's not that technical, but we're going to use it as a stepping stone for what's really important. Consider two functions. I'll call them big F of x and big G of x, such that the derivatives f prime of x and g prime of x are equal for all x, or even just for all x in some interval where we care about things. If that is the case, then I claim that there is a constant c such that the original function f of x is equal to g of x plus c. Now, c might be positive, might be negative, but it is constant. So plus or minus doesn't really come into consideration. And it turns out that in order to prove this, we don't want to try to look at these functions individually. Instead, we want to look at the difference of the two functions, f of x minus g of x. And I want to take the derivative of this difference and using the linearity of the derivative of f minus g is the derivative of f prime, minus the derivative of g prime. But since f of x and g of x are equal to each other, When we subtract them, we get 0. Right. This is a trick that commonly comes up. Um, if you're trying to prove something based on the fact that you have two expressions that are equal to each other, very often it's useful to notice the fact that they're equal to each other means that the difference between them is 0. So we try to get the difference between them into an expression like we did here. Right? Once we have done that, we can start relying on some theorems that we've built previously on what happens when things are equal to 0. Right. The derivative of a function is the rate of change of the function, how fast y is changing with respect to x. And if the rate of change is 0, that means that y is not changing with respect to x. The function is constant. So since the derivative of h of x is equal to 0, that means that h of x is equal to c for some constant c. Right? Could be positive, could be negative, could be 0. I don't know. All I know is that c is constant. But that means that f of x minus g of x is equal to that constant, which means that f of x is equal to g of x plus c, just adding g of x to both sides of the equation. All right. That takes us to our theorem. When we've set up accumulation functions, we have stressed that you could choose any value you want to put down here and nothing would change. Or very little would change. Here, I get that theorem stated cleanly. For any function in the family, f sub x naught of x, which is the integral from x naught to x of f of t dt. All right. The notation here is a little bit messy. F sub x naught, the subscript of the function, chooses the lower limit of integration, and that subscript defines the function. The x by itself is the variable. So x naught is the subscript that defines which function we are looking at, but they're all based around the same density function, little f of t. And that's why for any x naught, the derivative of f x naught of x is equal to little f of x. And so by our lemma, fx naught of x is equal to f sub any other x naught, like 0, plus our constant of integration. And of course, f sub 0 is the integral where x naught is 0. And so finally, we get to this tool, the indefinite integral, the integral of f of x dx without limits of integration. This is defined as the integral from 0 to x of f of t dt plus c. And when I say plus c, I mean literally plus c. We're going to spend several videos coming up exploring the indefinite integral in a little bit more detail. But for right now, I'm going to end asking you to think about how the fundamental theorem is going to extend to that. So I would like you to try to evaluate the derivative of the indefinite integral, integral 2x squared plus 3x minus 5 dx. Take a couple of minutes, see what you can come up with on that one, and I'll see you in the next video.